So in this video we're going to be looking at the Doppler effect. A speed camera works by sending out radio wave pulses which are reflected off your car, and it measures how the frequency of that wave has been shifted. In this video we're going to be seeing how that change in frequency is related to the speed of your car. So throughout this video until the end we're going to be considering sound waves, as you've got much more experience with sound waves and experiencing the Doppler effect with sound waves. So how you may have experienced the Doppler effect is when an ambulance drives past you. As the ambulance approaches you, its siren has a relatively high pitch, like ee-oh, ee-oh, ee-oh. And then when the ambulance has passed you and is moving further and further away from you, you hear it with a low pitch. And so just from hearing the noise, you can tell if an ambulance is approaching you or moving away from you. So this is due to the Doppler effect. So let's have a look at a demonstration of this now. Joe Wolf has produced some really good demonstrations of this topic on his PhysClip site. So what we're going to do now is watch Joe ride on a bicycle past a microphone. So Joe has a sound source on his bike which is producing sound with a steady frequency, and we'll see what's detected by the microphone. So this is showing the steady frequency on Joe's bike. Here's Joe approaching the microphone, so the microphone's the observer, and here's Joe receding. Now we're going to look at Joe again. This time Joe is wearing the microphone which detects the sound, and he's going to ride past the source. So the source is now stationary and Joe, the observer, is moving. So you can hear the steady pitch of the source. Here's Joe approaching the source and moving away from the source. So now you've observed the phenomenon, you've heard it for yourselves. Let's now look at the equations that we can use to describe what's going on. Now Joe explains this very well in his PhysClips, so let's go back to Joe.
Let's imagine two surfers watching the waves go by. With no relative motion, they both count the same number of waves in time t. So they both get a frequency n over t. Using F equals v on lambda, we find that in time t, both see a number of waves n equals vt over lambda. One of the surfers, call her the observer, now paddles towards the other with speed v sub o. In doing so, the observer overtakes more waves. In time t, she travels vot, so she overtakes vot over lambda extra waves. These add to the n equals vt on lambda seen by a stationary observer. So our approaching observer sees, in time t, vt on lambda plus vot on lambda. This gives her a higher frequency, f dashed. Substituting f equals v on lambda, we see that she observes a frequency increased by a factor vo over v. Here I am on the bike again. In the animation, not to scale, we see peaks in the sound waves spreading out. Approaching the source, vo positive, I overtake extra waves, so I hear a higher frequency. Later, as I ride away from the source, vo negative, fewer waves reach me.
So as you've just seen, if we have an observer moving towards a source, we can write down that the frequency observed by the observer, f dash, is equal to the frequency produced by the source, which is f, and then this is multiplied by the velocity of waves in that medium. So for sound waves travelling through air, they have a velocity of 343 meters per second. So that's what we're considering at the moment. With the speed camera, it uses electromagnetic waves, which have a velocity of 3.00 times 10 to the 8 meters per second through air and a vacuum. So we've got the velocity of the sound through the medium plus the velocity of the observer, which we give the symbol V subscript O, and then this is all divided by the velocity of sound through the medium, or the velocity of waves through that medium. So we've got the equation F dash is equal to F times V plus VO over V. Now, if the observer is moving away from the source or receding from the source, instead of having a positive sign in front of the velocity of the observer, we have a negative sign. So in the case where the observer is moving away from the source, we have the equation for the frequency observed by the observer, F dash is equal to F times V minus VO, all divided by V. Let's try a problem now where we'll be using this equation.
So the question is, a police car is stopped on the side of the road with its siren producing a steady frequency of 700 Hz. You approach and then pass the police car, travelling at 60 km per hour. The speed of sound in air is 343 meters per second. Part A, what frequency do you hear as you approach the siren? Part B, what frequency do you hear as you recede from the siren? Okay, so in order to do this, we're going to need to use the formula F dash. The frequency which is heard is the frequency at the source times V plus the velocity of the observer over V. So we know V is equal to 343 meters per second. Now the velocity of the observer, we're told, is 60 kilometers per hour. So that's 60 times 1000 over 60 times 60, which is equal to 16.67 meters per second. Now to do part A, we have this positive sign here as the observer is approaching the source. So the observed frequency F dash is equal to the frequency at the source, which we're told is 700 Hz, times 343 plus 16.67 over 343. So all we need to do is solve this on the calculator. When we do that, we get 734 Hz. Now for part B, we've now got that the observer is moving away from the source, and so we need to change the sign here. So we've got F dash is equal to F V minus V naught VO over V. So this is equal to 700 times 343 minus 16.67 over 343, and solving this one on the calculator, we get 666 Hz.